how we as humans have evolved throughout the years and how we've tried to improve the concept of trading value and exchanging value with one another. But somehow over these many years, throughout our whole evolution over these hundreds of thousands of years, we've still managed to face a lot of uncertainty and risk through any trade we do. So if we go back to our hunter and gatherer societies, typically when they wanted to trade items of value, they would typically enforce some force of violence, or they would provoke some form of social repercussion if that trade didn't go through, right? So if I'm trying to give you a bit of meat, you're trying to give me some berries, and you run off of my meat and don't give me any berries, something's going to go down. Back in those days, anything goes. But so as we've kind of evolved and we became more intelligent, we've kind of realized that we need trade, we need to go further afield, and with these kind of, as we do that, the societies have evolved and they become more complex, and our trade routes have become more distant. And with that, there comes even more uncertainty. So if we can't even socialize with our own groups and compromise within our own village structure, how do we get about that? So what people have done is that they brought about formal institutions. These institutions, such as banks, who would manage the likes of currency, loans, financing. We've got governments who step in and who implement monetary policies and other things like managing inflation. And of course, we've got the big corporations that are always there. But what happens whenever we bring these, whenever the internet came about, eventually these institutions, they came online. And essentially what happened then is that we now have platform marketplaces. We've got the likes of Amazon, we've got Alibaba, eBay, Rakuten. And all we've really done is we've just enforced more uncertainty and risk. But we've kind of leveled it out into a more level playing field. So these online institutions are now managing some of that risk and uncertainty, but with that we now have less control over our transactions and some of the data that we now put into these systems. So with these middlemen, they essentially become drivers for managing human economic activity during trades. So what does that mean? So whenever we're trying to manage our uncertainty and risk, as I mentioned, we have lower control over our transactions. And with that, a Nobel Prize economist, Douglas North, he once saw this as seeing institutions like our middlemen today. He saw them as tools that manage this uncertainty, but also help us connect and try and improve the trading between one another. So what does blockchain try to do to simplify this? Well, basically, blockchain tries to cut out the middleman. So how does blockchain cut out the middleman? Well, the blockchain operates on a peer-to-peer network. And what that means is that the blockchain is essentially a digital registry. In that digital registry, we have it's in the simplest form, a blockchain is just a big database, a decentralized database that stores a registry with a list of transactions and records. Those transactions or records, they are typically connected together. They're chronologically ordered, and they're connected together and secured by cryptography. So what does that mean? So whenever we add a new transaction to our block, we essentially have a secure way of knowing that this is going to be the next block on the chain and no one can tamper with this. It's an unforgeable entity. So one of the main innovations behind the blockchain technology is the fact that it uses a peer-to-peer network. What that means is that it uses inter-node communication. So everyone that signs up and joins the blockchain network, or whatever network it is, they basically have a copy of the registry. Whenever a new block is added, everyone gets told about this. And if anyone tries to tamper with that, a consensus rule will be applied and say, okay, you're trying to manipulate this block. Well, the majority of the users on this blockchain, we know that this is invalid, so it gets discounted. So it becomes very hard to tamper with a blockchain very easily. So moving on from the blockchain, what are some of the problems it tries to solve? So first of all, it tries to solve identity management. So think about Amazon, for instance. We don't know, we're not sure who we're dealing with. We know that whenever we want to buy something, say I want to buy like a smartwatch or a smartphone, the typical scenario is I'll go on Amazon, I'll look at the user, I'll see I'll read the reviews, I'll read the feedback, and I'll try and cobble together this fragmented information about some seller and try and decide whether this is a good buy or not. Similar to eBay, you go on, you see, is this guy a power seller? Is he got trusted reviews? And that's where you kind of make your decision on whether you want to buy that or not. But blockchain actually simplifies this, because whenever you don't need to know who you're associating with, you don't need to know who you're buying from. You just know that whenever a transaction is going to happen, you know that you're going to receive the funds, or you're going to receive some form of digital asset in return. And that's how the blockchain works. So with visibility, it tries to solve this because we don't have visibility into all of our transactions. As I mentioned, we have a lot of these central authorities, such as the big marketplaces, Amazon, we've got PayPal that we manage all our transactions, and we don't really know what's going on in the background. So what the blockchain does is it gives users more control. It gives us some of that control back, but also adhering to the same, actually reducing more of the uncertainty and also less risk, because we know that the blockchain is secure. And then again, the lack of recourse. This is what happens when something goes wrong. So I know PayPal has some policies in place that if I don't receive an item that I bought from some seller that I didn't know, then 30 days later they'll try and solve a dispute, things like that. But what if we have smart contracts in place for using blockchain? A smart contract is essentially a piece of code that can automatically run based on some information or policy decided upon by two users. So if I wanted to buy a smartphone from a user from across the globe on this blockchain, the typical scenario would be he would have a smart contract that would say, I will only release my funds until I receive the digital asset that I am receiving. This asset will also have a digital fingerprint, and it will be proved, and it'll have a full chain of supply, so we know that this hasn't been tampered with. We know we're exactly getting what we paid for. So where did this all start? Sorry. I'm going to give you some example demo applications that kind of enforce these ideas. So one of the cool ones that I saw was the self-sovereign ID, and this is really propelling the idea of identity management. And so this is an innovation by SecureKey and IBM and their blockchain, and they're using Hyperledger, which is kind of industry-level blockchain technology. And basically what they're trying to solve is whenever we sign up to a new website, we're passing in our information. Whenever we want to get a government document like a driver's license, or if we want to get our passport, we're just duplicating information. We're just giving these out to all these different authorities. Fair enough, there could be the government, but we don't know where it's going to end up. And also we run the risk of security breaches and things like that. What this tries to do is it implements a blockchain where users have more control over their data. What that means is that we can sign up to the blockchain, we can put all our information in there, but we can selectively say to which company and which authorities what parts of that information we wanted to give out. So for instance, if I was signed up to a driver license, I only want to give out my driver ID, my first name, last name, age, whereas if I was trying to sign up for something else, I don't necessarily need to give out all that information. So if a company says, hey, we need some information, they can sign up to this blockchain, they can say request using a public key, get my information, and a notification could pop up on my phone and it'll say XYZ authority is trying to access this information, do you comply? So this gives users more power, more control over where their data is going. Another cool example that I found, this one's really cool actually. So any of you that have used any online signature forms or anything, you know they're quite tedious, but DocuSign and Visa came together and collaborated on a proof of concept. And what they did was they had a smart connected car. So this is trying to disrupt the rental services. So if you go to another country, you typically say you want to rent another car or something. Well, what you have to do is you have to bring a shed load of information, you have to get an insurance policy set up, and it can take quite a long time. And in many cases, you try to do this in advance, and then once you get there, you find out about all these unhidden charges, and everything's not as black and white as you thought. So what DocuSign and Visa did is that they integrated this kind of dashboard. This is a cam in the dashboard. And basically what this allows the user to do is they just jump in a car of their choosing. They select the type of lease. So here they could select how many miles they're going to use. Then all they have to do is submit that, sign it, and then a smart contract is initiated. What that means is that it's going to go through DocuSign. They're going to verify who the user is. And then it's eventually going to be passed on to Visa. So they've got this smart contract in place saying user X is going to borrow this car for 1 week. And as soon as that contract is over, the smart contract is a piece of code that will run automatically. And after that week, that time period that has been defined, the policy that's in place, that'll automatically discontinue. So it means you have faster feedback, and also it's a bit more clear on what you're doing. Visa took this another step further by integrating all their payments into this smart connected car. So whenever you go roll up to a drive-through, or if you go to a restaurant, or if you're driving past tolls, you don't even have to wait and stop. This automatically comes out of your car. It's all connected. I think it's a pretty cool piece of tech. Another one is the Brooklyn Microgrid. So this one is from LO3 Energy, and they collaborated with the Brooklyn Microgrid. And basically what they've done is they've allowed communities to join a blockchain and join a peer-to-peer network where the neighborhoods that are generating their own electricity can also give back, not to the grid, but to other neighbors, anyone that's connected to their network. Because typically whenever you join the grid, you're basically paying a set price, right? You're getting an electricity bill and you have a set rate. What these users are allowed to do is that if they have any spare energy, they're able to share that among their neighbors, and they can sell it at a much cheaper price. So not only are they making the environment more green, but they're also giving back to their own community, which I think is just awesome. But the list goes on. There's hundreds and possibly thousands of different implementations of how the blockchain is used and where we can go for it. For example, the digital voting. I know the Democrats and Republicans were very questioning the legitimacy of the voting system back in 2016. And a lot of experts say that the voting system, who knows if it's guaranteed, who knows if it's not hackable, who knows if it can't be tampered with. But a blockchain would solve that problem. We have supply chain management. So any of you know about the horse meat scandal? Well, if we had supply chain management, what we could do is that every item that comes off the shelf, it could be digitally fingerprinted and tracked, and we could know where it came from, who it's been processed with, who the farmer was, everything. That could be all digitally tied, and it could be cryptographically secured, and nobody can tamper with that. And moving on, we've got loads of other applications, healthcare, such as smart contracts, proof of delivery. So if you're getting private healthcare and you get issued receipts, this will automatically come through smart contracts. So there's no signing forms and waiting months to get your insurance claims sorted. It's all done automatically. Money lending services, I think this is a really innovative one via smart property. So typically we go to wonga.com or some website to try and lend some short-term lending scheme. Basically they apply some ridiculous interest rate. So what smart property allows us to do is that users, we can use our own digital assets as collateral. So I could just say to anybody in this street or anybody on the network, I don't need to know who you are, where you come from, what you do, but a smart contract will be in place to say, I will lend you £1,000, but in return, I'm going to use say 2 of your iPads as collateral, one of those digital assets that are up to date on that blockchain. And I think that's pretty powerful because we now don't need to go to all these centralized authorities. We've now got the availability of every user that's on the blockchain. And there's some other ones like registering music copyright was a big thing with like some of the superstars and stuff. But the possibilities, they truly are endless. But it's still in the infancy, and I don't want to try and paint a pretty picture for blockchain because there is some problems and there is some difficulties. There's scaling issues, things like that. And I think we're eventually going to get there, but I don't think we're that close. It's still going forward. So how did this all start? Well, in 2008, Satoshi Nakamoto, a person or persons, we still don't know who these people are or person, released a white paper titled Bitcoin, a peer-to-peer electronic cash system. In that white paper, he described the implementation spec of the blockchain, and that's where the blockchain came about. But initially what he tried to do was to fix the double spend problem. And by doing that, we've now got access to the blockchain for his implementation. So in 2009, January, he mined the first Bitcoin block. And since then, Bitcoin is now at a ridiculous market cap of in the billions. It's crazy. So live demo time, no pressure. So I just got the halfway card, so figure that I've spent a lot of time rambling on there, but it should be sweet. So I'm going to spin up my app. So basically this is a demo application that I've built using Node.js in the background, and I've got a React front end. So I'm just going to go ahead and create a peer. I'll get into the details of a peer later on, but just to highlight what a blockchain is. So this user is connected, and if I show his blockchain, you can see that the first block on our chain is our genesis block. Every blockchain has a genesis block, and it's the first thing that you have on the block. So here we have some form of data. So typically that if it was Bitcoin, this would be like a transaction, a to and from address, and the value, the amounts. But for simplicity, I've just kept this an arbitrary data field, which can be anything. Every block has a timestamp so that it can be uniquely identified and chronologically ordered in the blockchain. And as well, we have a previous hash and a hash value. These values are used to calculate the next block on the chain, to calculate the next hash on the chain. So if I bounce over to my slides again, and just show you what that looks like in code. So you can see here I have a constructor. So I've got a block class, and in my constructor, I have these various attributes. So I'm passing in the index, the timestamp, the data, and the previous hash. And what we do is whenever we have this information, we then go and calculate this block's hash. So some of the hash properties. So the same data, so some of the characteristics of a hash. So the same data results to the same hash. The hash is easy to compute. It's unable to convert the hash back to the data. It's almost very hard, it's almost impossible to convert data back from a hash and try and work out what the data was originally. Slight changes in the data will result in big changes to the hash. So here I'm using a module called crypto. I'm creating a hash using the SHA-256 algorithm, and I'm passing in my information. So every block will go through this process whenever it's being created. So I'm going to go on and create a block. Amit. Perfect. So that's added a new block to our blockchain. So we can see here that our new hash starts with these leading zeros. So what that means is that whenever we are adding a new block, we need to have some way to verify that this block is authentic. So if I jump back to my slides, whenever we create a new block, I have a peer create block function, which says to the chain, okay, I'm going to create a block. The create block function will jump into a proof of work algorithm. The proof of work algorithm basically initiates a new block, so instantiates a new block, and it calculates the next hash. Whenever we're adding a block, what we're essentially doing is we're mining a block. Whenever it goes through this proof of work algorithm, it goes through and sets a loop. It sets an iterator. It'll keep looping and iterating through this iterator and creating a unique hash each time. It's going to keep doing this until it conforms to some form of policy. And that policy is the difficulty. The difficulty here is 3 leading zeros. So what that means is that this avoids people being able to spam your blockchain, right? So it adds some computational power element to creating a block on your chain. So the difficulty here is 3 zeros. So what that means is that because it's going to generate a new hash, and it's going to keep constantly doing that, we use a nonce value to increment each time. So through this loop, what we're saying is, I'm going to create a hash, and if this hash doesn't have 3 leading zeros, we're going to go through and increment our nonce value. And if you noticed before, the nonce value is passed in as one of the attributes that define what the next hash will be. So what we do is we keep incrementing, so it'll go 0, 1, 2, 3, until it finds a hash that matches, that has 3 leading zeros. So here's an example of that. So whenever I create a block, it goes through and it's generating all these hashes, and you can see here that the last block that was created, it's got the 3 leading zeros. And that's just adding some computational power to slow things down, make sure nobody can spam transactions on your network. So after we've added this block to our chain, what we do is we check if the new block is valid. Firstly, we just have to check if the previous block index is the next block's index. We just want to make sure that the previous block was, the new index matches the one of the previous block plus 1. So the next block in the chain is going to be the previous block plus 1. If it's an invalid index, we return false, so we know that this isn't valid. The next check we do is we pass in a previous block hash, and we just double check that the new hash that we've just generated is now matching our previous block's hash. If that doesn't match, we return false. And then we go through and check if our hash is valid. So what we do is we just, as a sanity check, we go through, create the hash with all our new values that are now valid, and we double check that everything is matching, which is good. So I've got a scenario here where I'm going to show how the peer-to-peer network works. I just need to quickly restart this server. So I've got these three users, Amit. I'm going to create another peer, Carl. Don't know where I'm getting these names from. Tim. So here, each one of these users aren't connected yet on my peer-to-peer network on the blockchain, on their blockchain. So what this means is that they all start off with the same blocks, right? So they've all got their own version of their Genesis block. If I go into Amit and I add a new block, so I'm going to say Amit, next coffee, 1. I'm going to add a new block. You can see here, if I jump down to Carl, nothing's been updated because they're not connected yet. If I bounce over to Amit again, I'm going to add another block. Amit, coffee, 2. Add this to our block. So you can see here, our blockchain has been updated on Amit's. Carl and Tim haven't received those updates. So what I can do with Carl, I can jump over and I can add him as a peer. So whenever I've added Carl as a peer to Amit, this means that he will receive my blockchain. And the reason for that is because my blockchain has been validated. It's went through all the hash function, and all the next hashes are all completely valid. So what this means is that because Carl's blockchain is out of date, which means it's out of sync, there isn't enough blocks to compare against, he gets an updated version of mine. So if I bounce over to my terminal here, see that I've added these blocks through Amit. I've added a host, which is, this is just a WebSocket connection. It connects to Amit. Whenever we've initiated this connection, Amit says, I don't need to update anything, but hey, Carl, he's requesting the chain. He's requesting the chain because he doesn't have any of the previous blocks. So if we go back to our example, I bounce over to Tim, and I add a block. So Tim, coffee, 1. You can see here that he isn't connected to any peer, so he has 1 block in his chain. If we go over to Carl, we add Tim to our block. You can see that Tim's blockchain hasn't changed or nothing. It's because Tim has just joined the network. He's tried to add blocks, but nothing's happened. We bounce over to Tim, and Tim has now received the most up-to-date chain. So what that has done is, whenever Tim has joined this peer, he's basically sending out a request and saying, hey, what's the most up-to-date blockchain? And he receives that. So you've probably noticed that I'm sitting here adding coffee prefixes to all these things. So as developers, we're generally fueled by coffee. And whenever we are hanging out with our friends, we typically want to keep track of who's buying what and who's paying for what coffees. So I'm going to say Amit came up with the idea that he wanted to keep track of everyone's payments. So what Amit did is he created a blockchain. He got all his friends to join in, and they now just put in the values of who owes what. So Tim is going to say he owes 2 coffees. Great. So Carl and Amit, Amit hasn't received that yet because he isn't connected to Tim. So if we both bounce over to Carl, he received that because Tim is a direct peer to Carl. So if we add Tim to Amit, we should hopefully see that updated. So Tim has now, his entry has now been added to Amit because Amit's blockchain was out of sync now. So
has Tim's first coffee disappeared?
Has Tim's first coffee disappeared? Tim's first coffee, yes, it disappeared because if you remember, whenever Tim joined the network, what happened was that he sends a request out to all the peers that he's trying to connect to, and it says who's got the most up-to-date blockchain. So what happens is that because Carl's blockchain had more entries, it means Tim's was behind, so his is no longer valid. So now that they're all connected and they're sharing coffees and keeping track of everything, Carl's going to add in his own entry. He's going to say he owns 9 coffees. So you can see here, everyone's got this entry, perfect. But what do we want to do? What happens if Carl wants to change this or mutate this in any way? So we can actually do that. So Carl isn't saying that Amit owes 2 coffees. He's going to say that Amit owes 7 coffees. And what that's going to do is it's going to invalidate this hash, right? So we put in new data, and because the data that's passed into our hash function is one of the attributes that computes the next hash, well, that's going to be mutated, which is going to invalidate all the rest of the hashes in the chain, because every subsequent hash on the block is generated from the previous hash of the previous block. So if I mutate this, you can see here that I have a number of invalid blocks. If I bounce over to Amit, he doesn't think anything's going wrong. That's because he's got the most up-to-date valid blockchain. So what does Carl have to do in that scenario? Well, this is what we call a 51% attack. What this means is that users, anybody that wants to try and forge or manipulate or change a blockchain in any way, what they need to do is they need to outpower the computational power of every peer on the network. So whenever peers are adding new blocks, they typically mine them, they go through that hash algorithm, and it applies the proof of work. That proof of work, having those 3 leading zeros, if we increase that to have maybe 5 or 6 leading zeros, that'll increase the time to compute those hashes, because whenever we're generating a new hash, it's just an arbitrary hash function. So it takes a longer time to try and generate those. So what Carl has to do is that he needs to simulate he needs to go through and try and outmine all the rest of the peers. So what would typically happen in like Bitcoin, for example, they would have like a pending transactions bucket, and these would be pulled off and then chronologically ordered in that order. But here, for simplicity, I'm just going to simulate how Carl can outmine his blockchain and theoretically change and update Amit's. So he's changed Amit's to 7. He needs to outmine this. He needs to mine the next block, and he needs to keep mining the next block. He needs to mine every subsequent block. So now Carl's blockchain is up to date. However, the changes haven't been published yet. You can see that these guys have the up-to-date chains, whereas Carl still has this entry of Amit, who owes coffee 7. So the next time Carl adds something to the blockchain, he's going to say Carl coffee. He owes nothing because he's being really tight. He's going to add another block, and we can see that next entry. So what happens to Tim and what happens to Amit? Well, they're going to receive this, and now he's basically simulated a 51% attack. What that meant was he's went through, he's computationally outmined all the rest of the peers, and he's just replaced their blockchain with his forged version, which obviously isn't great. So how do I do that? So if I bounce over to my peer node, I basically used, on the front end, each one of these peers has just a REST API, just to update some of the blocks and add new peers and mining new blocks. But behind that, every time a peer is added, they initiate a WebSocket connection. And in here, we have a message handler. So I have a broadcast function that will say, hey, I've added a new block. So every connection on our peer-to-peer network will receive this message, and we'll see what the type is. So we can say, is the case, is someone requesting a new block? So we can request the block. Or is somebody requesting a new chain? We can send down a new chain. And again, we can process these as well. So whenever I request a block from our node, I'm basically saying, hey guys, I've got this new block, can you give me the latest one? Whenever we go to our broadcast message function, it loops through every one of our peer sockets. So we just have a top level variable that inserts every one of those sockets and every one of those connections essentially. Just loops through and says to everyone, hey, I'm going to request a new block here. So they will receive that message, and they will fulfill that requirement, and they will pass down the next block in the chain. And also, whenever I bounce over to my terminal here, you can see here that I'm logging out some information that's been going on. So Carl is checking if the blockchain is valid. Blockchain is valid. So he's going to create a new block. So whenever we went down and Carl was mutating our blocks, you can see here that he has mutated everything, and we're calling him a lead hacker. We can see the hash that he's been given. So he's just simulating that 51% attack. So through that process, he went through, he had to mutate every subsequent block. It tells us that the block's been tampered with, and this is the new chain. Whenever the blockchain is valid, we've checked that Carl's blockchain is valid, he's creating a new block. And then whenever Amit goes through and he requests his new chain, whenever Carl has added that last block, everyone gets updated and they just don't think anything's wrong because of that 51% attack. So he's essentially outmined that network. I'm getting weighed for out of time, so yeah, that's pretty much it. If you have any questions, I'm going to add all this source code up into GitHub, and you can pull it down and play about with it. But thanks very much for your time for listening.